good. And then I will share my screen. So share entire screen. Perfect. Here we go. Good way to spend a Tuesday morning, right? It's supposed to get cold the next few days, I saw, so good time to be inside studying for a final exam. All right, so this review is posted to D2L in its entirety, and I would recommend giving this a shot ahead of time. If you haven't already, though, let's take a look here. And the way that she's laid this out is some of these are actual questions, and other ones are just kind of bullet points where it says, we'll just discuss the concept a little bit. So the first question deals with balancing equations, and this is a combustion reaction. It says balance equations using the smallest set of numbers, and she should have put here whole numbers because we don't want to have any fractions. And so you start out with this molecule which has all kinds of carbons and hydrogens and oxygens in it. And then, of course, we add oxygen and we produce carbon dioxide and water. I've gone ahead and I've determined what the molecular formula for this compound is. So that means I added up all the carbons, the hydrogens, and oxygens. And the molecular formula is C3. So there's 3 carbons. There are 8 hydrogens and 1 oxygen, like that. So what she says here is the strategy that you should take in balancing these types of equations is to first balance the carbon, then do the hydrogen, and always save oxygen. Always do oxygen last. Leave that for the last 100% of the time. So we have 3 carbons, and if we have 3 carbons, we're going to need to have 3 carbons over here. So we have 3 carbons there. If we have 8 hydrogens, there are 2 hydrogens in water. So what times 2 will give me 8? And the answer is 4. Now I will tally up all of the oxygens in my products over here. So I have a total of 4 from the water, and I have a total of 3 times 2 from the carbon dioxide. So that makes a total of 10 oxygens on this side. And so, aren't there 4 carbons? Oh, did I put the wrong molecular formula? I did. You know why I did that, Marina? Because I'm looking at 2 versions of the review. So let's fix it here. So the molecular formula is C4. Thanks for pointing that out. It's C4H1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10. Oh, there we go. Okay, so let's get started here. So we have 4 carbons, sorry. We have 10 hydrogens, so 5 times 2 will give me 10 hydrogens. Now we tally up all of the oxygen, so I'll fix this. Okay, and we have 4 times 2, which is 8 oxygen atoms from the carbon dioxide, plus 5 from the water. So that's 8 plus 5, which gives me a total of 13 oxygens. So then what do I put? What times 2 gives me 13? And the answer is 13 over 2. So I would put 13 over 2 here. And then what do I want to do? I want to have whole numbers. So I'll multiply the entire thing by 2. So I'll take this whole expression and I'm going to multiply the whole thing by 2 to get rid of this fraction here. So then I would have 2 of this molecule. I would end up with 13 here. I would end up with 8 and 10. So let's fill those in. So 8 and 10. And that is how you balance a combustion reaction. And we looked at several of those in our class. So let's take a look at the next question, which deals with density. You have to have the formula for density memorized in the old noggin. So density is equal to mass over volume. It says here the density of methanol is 0.793 kilograms per liter. What is the mass of 6.75 liters of methanol? And so we have to be able to rearrange this formula and say that mass is equal to density times volume. And so we just plug in our numbers, 0.793 kilograms per liter, and I multiply by the volume, which is 6.75 liters. You can see that the volumes cancel out, and I end up with, and I'm going to do the calculations in real time here, so 75. and I end up with 5.35 kilograms. And there should be 3 significant figures in this answer, right? Because I have 3 significant figures in my density and 3 significant figures in my volume. The next one just involves using the periodic table. So this question says, given the formula of a chemical compound, determine the molar mass. If you've been keeping up with the practice problems over the course of semester, you should have done this Avogadro's number of times, meaning going to the periodic table, looking up the mass of a barium atom. So I go to my periodic table. Barium is element number 56. It has an atomic mass of 137.34 grams per mole. Then I look up the mass of an oxygen, which is 15.99 grams per mole. Of course, there's 2 of those, right? I have 2 hydroxides, so 2 oxygens, and then I look up the mass of a hydrogen, which is 1.008 grams per mole. And of course, there's 2 of those. So when you tally all that up, and I'm not going to multiply them by 2, I've already gone ahead and done the work. But when you tally all that up, it should equal 171.35 grams per mole. All right, there we go. So everybody should be able to calculate a molar mass. And again, that's something that, if you kept up with the practice problems, you've done that many times already. So that should just be, money in the bank, free points, right? The next one, she doesn't have a question here, but she just says, thinking about density and the concept of floating. And she says, if something floats in water, it's because its density is less dense. So if you think about something that's lighter than, or has less dense than water, like maybe a piece of wood, a piece of pine wood, not all woods are less dense than water, but if you have a density, so we'll put density is less than 1.00 grams per mil, it's going to float, right? And if you have a density that's greater than water, then it's going to sink. And that's not meant to be a complicated concept. It's more the idea of, do you understand what the heck, density means, okay? The next one talks about given a balanced chemical equation, number 5, and the amount of reactant, you should be able to determine the amount of a product that's produced. And of course, this is a balanced equation that's given to us. So we have all our stoichiometric coefficients. So we have 3, 1, 3, and 2. Now let's take a look at how we would use a balanced equation in a problem. It says if you have 6 moles of aluminum oxide, and it reacts, how many moles of copper 2 oxide are produced? And the way that you would do that is you would build or make a conversion factor that relates the number of moles of aluminum oxide to the number of moles of copper oxide. And you can see the ratio is for every 1 mole of aluminum oxide that I consume, I produce 3 moles of copper oxide. Now, I'm sure many of you can just do this in your head, say, okay, well, 6 times 3 gives me 18. But let's do this using dimensional analysis. So if I have 6.0 moles of aluminum oxide, I didn't leave myself a lot of room here, did I? I know that from my balanced equation, for every 1 mole of aluminum oxide that I use up, I produce 3 moles of copper 1 oxide. You can see that moles of aluminum oxide cancel, and I think everybody can multiply 6 3 times in their head, and you end up with 18 moles of copper 2 oxide. So what's the take-home message from this question is knowing how to use a balanced equation to make a conversion factor. Question number 6. Given a chemical formula and the amount of moles of a compound, determine the number of moles of a specific component. Let's take a look at the question. It says here, how many moles of hydrogen atoms are there in 0.75 moles of sucrose? This involves a little bit of dimensional analysis because we know that in 1 mole of this molecule, sucrose, which is table sugar, in 1 mole of sucrose, I have 22 atoms of hydrogen. So let's see here. If we have 0.75 moles of sucrose, C12H22O11, okay, we know that in 1 mole of sucrose, C12H22O11, we know that we have 22 hydrogen atoms, okay? That's how many atoms we have. And actually, I should put 22. Why don't I put like this? Come on. 22 moles of H atoms, like that. So you can see that moles of sucrose are going to cancel out, and I end up with the number of moles of hydrogen atoms, which would be, I've already gone ahead and done the math here. You get 16.5, but there should only be 2 sig figs in, actually, yeah, there should only be 2 sig figs in the answer because there's 2 sig figs here, so that would round up to 17 moles of H atoms. All right. There we go. Another, little bit of dimensional analysis. The next part is about the history of the atom. I'm not going to spend a whole lot of time on these. Suffice to say that you should understand the Rutherford gold foil experiment. So that's where Rutherford took a piece of gold foil, and it had gold foil is made up of gold atoms. So we'll put some gold atoms here, This is not to scale, obviously. And what's inside all of those atoms? There's a nucleus, right? And he determined that an atom was mostly empty space because he fired alpha particles. So he took alpha particles and he fired it at the gold foil. And an alpha particle is just a helium nucleus, but he fired them, right? And most of them went straight through, but every once in a while, one of them would bounce back, right? Or it would ricochet off. And that's how he discovered the nucleus. Then Chadwick discovered the neutron, and neutrons are neutral. They have no charge. And then the whole thing about J.J. Thomson and the cathode ray is that Thomson used what he called a cathode ray tube, and he took a stream of particles, which were electrons, which are generated from electricity, and then he subjected them to a magnetic field, and he found that the stream of particles was affected by a magnetic field, and it was also affected by charged plates, and therefore he determined that electrons had a negative charge. And that you should also know that an electron is about 2,000 times smaller or lighter in terms of mass than a neutron or a proton. All right. This question here deals with chapter 9. So this is a question from chapter 9. This is about the only kind of question that you'll ever see from chapter 9 on a final exam, which involves balancing a nuclear chemical reaction. So it says, given a nuclear chemistry reaction, determine the missing nuclide. So all you have to do for these is balance the mass number and balance the atomic number. Now, you can see it's not written really big here, but here's the reaction arrow. So we have Einsteinium 253 plus an alpha particle. And even if you don't know what an alpha particle is, you can see that if you look at 253 plus 4, what's 253 plus 4? Let me get my, I don't need it. It's 257. All right, it's 257. So that means the mass numbers of my products have to add up to 257. Well, I've already got 1 here. So what plus 1 gives me 257? And the answer is 256. Okay, so that's balanced. And then I look at my atomic numbers. I have 99 and 2. 99 plus 2 gives me 101. Now, what plus 1 gives me 101? And the answer is 100. So my atomic number must be 100. So then I go over to my periodic table and I see the element Fm. This is element number 100. And there we go. And that is the missing nuclide. Nothing more to it than that. The next one is just a little bit of a refresher on the names of the families or groups. Families or groups, these are the synonymous. So the names of the families in the periodic table. Group 1A is the alkali metals. Group 2 is the alkaline earth metals. Other groups that you have to be familiar with, you should know what transition metals are. So anything that's in the D block is considered a transition metal. Then we have the halogens, of course, and we spend a lot of time talking about the halogens, which are fluorine, chlorine, bromine, and iodine. And then the noble gases, which is the last group, group 8A. And the noble gases, they are very unreactive. Very few compounds formed from the noble gases. Okay, let's move on from there. Question number 10. Excuse me. Question number 10 says, given a mass of a compound and the volume of solution, determine molarity. So we use the big letter M for molarity. So molarity is equal to the number of moles of solute divided by the liters of solution. Let me just clean that up a little bit there. All right. So it says here, what is the concentration or molarity? Right? Concentration is the same thing as what is the molarity of a solution prepared by dissolving 8.54 grams of sodium fluoride in enough water to make 1,635.0 milliliters of solution. So the first thing that we need to do here is a little bit of conversion, because we need moles and we're given grams, and then our volume is in milliliters and we need to convert that into liters. Let's do the conversion of the volume first. And we know that, and I'm sure most of you can do this, or all of you can just do this in your head, and there's no problem with that, but I'll just use a conversion factor here, and we know that there are 1,000 milliliters in 1 liter, so this is equal to 1.6350 liters. Then we'll do a conversion for the number of grams of sodium fluoride, and we will convert that into the number of moles of sodium fluoride. I've already gone ahead and looked up the molar mass of sodium fluoride, or the formula mass, so 8.54 grams of sodium fluoride. And I know that I have 41.99 grams of NaF in 1 mole of NaF. Anyhow, you punch that in your calculator and you end up with, I did it all in one fell swoop here, so let me just 41.99. So you end up with 0.203 moles of sodium fluoride. And then to calculate the molarity, we just use this formula up here. So our molarity is going to be equal to the number of moles, 0.203 moles. So we're going to have 3 sig figs in our final answer, 6,350 liters. And our molarity should be equal to 0.124 molar. And there you have it, folks. Okay, dilutions, a real chestnut, a real favorite of Chemistry 101 students is dilutions. And it says here, if I want to make 1.5 liters of 1.55 molar sodium chloride, but have only 10 molar sodium chloride available, how many milliliters of the stock solution do I need to dilute? And for this, we can use the formula M1 V1 is equal to M2 V2. Sometimes you see this written as C1 times V1 is equal to C2 V2, depending on the textbook. Molarity and concentration are saying the same thing. And so I want to rearrange this for how many milliliters. So I'll solve this for V2. So I'll put here that V2 is equal to M1 times V1 divided by M2. And the way that I will do this is I will call this my M1, the 1.55 molar. I'll call this my V1, and then I'll call this my second molarity, like that. So I'll plug in all the numbers. And of course, we're going to end up with liters, aren't we? So 1.5 liters multiplied by 1.55 molar. And then we're going to divide that by 10.0 molar. You can see that the units for concentration cancel out. Let me just double check my work here. 1.5 times 1.55 divided by 10. That gives you 0.23 liters. But then I need to convert that into milliliters. And to do that, we just multiply by 1,000. So multiply. I'm going to kind of do it in two steps with my equals, with my answer here. So we know that in 1 liter we have 1,000 milliliters. So liters cancel out, and I end up with 230 milliliters. And there should only be 2 sig figs in that final answer, because I only have 2 sig figs for this volume. Question number 12, moving right along. It says, given a volume and a percent, determine the mass in grams of the solute. So it says here that you need to prepare 8 liters of an 8% mass over volume solution of sodium chloride. How much sodium chloride do you need to weigh? The first thing that you need to know is the formula for percent mass over volume, and percent mass over volume is equal to the mass of solute in grams divided by the mass of solution in milliliters, like that, and then multiply by 100%, like that. So if we want to rearrange and solve for the mass of solute, so I'm just going to do it all here in one step. So if I want to rearrange mass of solute, which is our mass of sodium chloride, I'll put it in brackets. I'm just rearranging the formula here. That's going to be equal to the percent mass over volume, and then multiplied by the, oh, did I put mass of solution on the denominator? I meant volume of solution. There we go. Yes, there we go. Yep, back to my red pen here. And let's see, so my percent mass over volume, which is 8%, and I want to make an 8 liters of solution. So I'll say that this is 8,000 milliliters, and I'm just converting that in my head. Sorry, I was doing the formula first, wasn't I? There we go. Okay, yeah, times my volume divided by my 100%, and therefore let us just plug in some numbers. So we have our 8% multiplied by the volume. Again, I'm going to convert that to milliliters. So 8 liters is equal to 8,000 milliliters, and then I divide that by 100. And when you do that, you end up with 640 grams of sodium chloride. I think that anybody here can rearrange the formula, right, of percent mass over volume to rearrange and solve for the mass of solute. I don't think that's super challenging, okay, to rearrange and solve for this. So I think the hardest thing about this problem is memorizing the formula, and you do have to know this formula. Percent mass over volume is equal to mass of solute divided by volume of solution. All right, there we go. So let's move on from there. Let's talk about sig figs. Always a crowd favorite. Significant figures. So if I have leading zeros are not significant, right? So I have all this spinach here. All of this is insignificant. So this number only has one sig fig. If you look at the next question, or the next number, the leading zeros are insignificant, but any zeros following a non-zero number after a decimal place are all significant. So all of these zeros are significant. Okay, so this one will have 4 sig figs, the 1 and the 3 trailing zeros. The same thing applies to this one here, but now I only have 1 zero after the non-zero, so I have 2 sig figs. This one is a rule that it depends on the book that you look at, but the way that we do it in this class is if you have trailing zeros and no decimal place, you have only one significant figure here, which is the non-zero number, but as soon as you put a decimal place in there, everything to the left of the decimal place becomes significant. Yeah, so you have to be rock solid on your significant figures. What if I asked you guys a question, and you can either unmute your mic or you could type in the answer. I'll ask you a question to see if you're listening to me. So if I had 1.320 times 10 to the 19, could anybody tell me how many significant figures are in that number? Yeah, so you're all three of you are perfect. Good. Okay. Why is it only the students that don't need the review that show up to? I'm just kidding, okay? My great students here. Okay, anyhow, so I have 4 significant figures. Yeah, absolutely. You're all right. Perfect. Thank you for that. Okay, let's talk about pH for a second here. So it says you should be able to determine pH if you're given a hydronium concentration. Blood has a pH ranging anywhere from 7.35 to 7.45. If a patient tests with a concentration of hydronium or protons, remember that we can write H plus or we can write hydronium. They are the same thing because H plus does not exist in solution. It actually solvates with water to form hydronium, but you can represent it either way. So what I'm saying is that you can say this or you can say this. They mean the exact same thing in chemistry. So if a patient tests with this concentration of H plus, how does the pH compare to the normal range? Well, let's figure it out. And we know the formula for pH, which you have to have memorized, which is pH. Hold on, Hedera. There you go. pH is equal to minus log of the concentration of H plus or the concentration of hydronium. These are the exact same thing. Don't you just love chemistry? One of my students put it this semester. Chemistry is just a matter of learning all the rules and then learning all of the exceptions to the rules, right? Nothing more than that. Okay. Anyhow, so let's plug some numbers in here and we'll say pH is equal to the minus log of 1.35 times 10 to the minus 9. Make sure you're able to do this in your calculator. And different calculators calculate, or I should say the sequence of events when you're determining or calculating a log are different depending on the calculator. So let's see here. And I have 3 significant figures in my concentration. That means that my final answer should have 3 numbers past the decimal place. So I didn't even do this one. So I'll put in here 1.35 times 10 to the negative 9. I'll take the logarithm of that. And you should end up with, excuse me, the pH is equal to 8.870 is what it would be. So you can see this person's pH is pretty high, so I would say this person is going to look something like this, okay? I'd say they're going to look a little something like that. So they're not feeling too hot. Okay, they're feeling a little too acidic. That's way outside the range. They must have got poisoned or something. Anyhow, next one. It says you're given the formula for a compound, determine the formula for a different iteration. And so what's going on here in this question, it says if potassium hexafluorosilicate is K2SiF6, what would the formula be for magnesium hexafluorosilicate? And there are all kinds of polyatomic ions that we don't cover in Chemistry 101, but you need to figure out what the heck a hexafluorosilicate is. Things like sulfates, nitrate, right? These are things that everybody in general chemistry knows, but you need to figure out what the charge of this hexafluorosilicate is because everybody by now should know what potassium is, and potassium is K, and potassium is in group 1A, therefore it has a charge of potassium plus, right? It likes to lose 1 electron to become potassium plus 1. Now, if I have K2, that means that overall there's a charge of plus 2 associated with my cation. That means that the whole charge of the SiF6 or the hexafluorosilicate must be minus 2. So this tells us that the polyatomic ion for hexafluorosilicate is SiF6 2 minus. Now it's asking us, what would the formula be if you had magnesium hexafluorosilicate? There's a lot of work in this one. But magnesium is in group what? Group 2A. Group 2A. And so it likes to take on a charge of plus 2. Well, if magnesium is 2 plus and hexafluorosilicate is 2 minus, they're going to come together in a 1-to-1 ratio. And therefore, the formula of magnesium hexafluorosilicate would be MgSiF6. So never be afraid if you see a polyatomic ion that you don't recognize. There's all kinds of polyatomic ions that we don't learn in Chemistry 101. In fact, there's many polyatomic ions that I don't know or I've forgotten along the way. but you can oftentimes determine what the charge of that polyatomic ion would be. The next one is just a matter of knowing your nomenclature, and I think the hardest thing here would be remembering what a sulfate is. Okay, so you need to know sulfate, nitrate, carbonate, all those polyatomic ions that I had highlighted in pink on that famous slide way back when we were studying nomenclature. So you need to know that a sulfate, oops, that's not sharp. A sulfate has a charge of 2 minus, and it's SO4 2 minus. You also need to know what the stock naming system is. And if you're like, what the hell is that? That is using the Roman numerals. And what that means is that it's nickel with a 3 plus charge. So if I have 3 plus and 2 minus, how would I combine those? Well, if I multiply this by 2, and if I multiply this by 3, then I get -6, and I would have +6, and they would cancel each other out. Therefore, the formula must be nickel, and I need 2 of those. And then sulfate, since it's SO4 and the 4 is a subscript, I have to put all of that in brackets, and then I will put my 3 outside like that. So this will be the correct formula for nickel 3 sulfate. The next one is just turning it around, doing a 180, and it says, if I give you a formula, determine the name for this. And again, you have to be Johnny on the spot with the polyatomic ions. Could anybody tell me what the name of this polyatomic ion is? Again, you can unmute your mic or you could type it out. Either way is fine with this guy. Who wrote something? Carbonate. Absolutely. Yes, this is carbonate. So what's the charge of a carbonate? So thank you, Hadira. That's perfect. So let's write it out here. We'll put CO3. Does anybody remember? It's okay. I understand what you meant. It's carbonate. Remember, it's a chemistry exam, not a spelling exam. What's the charge on a carbonate? Does anybody know what the charge is on a carbonate? Yes, absolutely. It's 2 minus. You have to have this memorized. Must be memorized. As same thing for all of the polyatomic ions, right? The ones that I asked you to memorize for this course. So if I have a carbonate and there's 3, so I have 3 times -2, that gives me -6. So that means my cobalt must overall be +6, but there's 2 of them. So +6 divided by 2, that means that each one of these cobalts has a +3 charge, and cobalt is a transition metal. So I will use the stock naming system. So this must be cobalt 3 carbonate. Cobalt 3 carbonate, like that. And there you have it, folks. Boom. Highlight it. All righty. Let's move on and take a look at the next question. Question 18. It's practically over, right? Given several substances, determine the compound who can hydrogen bond. Which substance will have hydrogen bonding? In order to have hydrogen bonding, she has it highlighted here, the hydrogen needs to be attached to an oxygen, a nitrogen, or a fluorine. Remember, don't fall into the trap of thinking that, maybe these could be hydrogen bonding because you have OH in here. These don't count because they're ionic, right? OH minus, shoot, I keep doing that. OH minus is hydroxide, right? That's hydroxide. That's not going to be involved in a hydrogen bond. Now, if I look at CH3F, I have a fluorine, but the fluorine is not bound to a hydrogen, right? Because if I look at the Lewis structure of that molecule, it would be this, right? So I have a CF bond, but I don't have an HF bond. This next one, when I have CHO like this, again, that could be written like this. I have a CH3, then another CH2, then I have a carbon with a double bond like this and a hydrogen. So this is a carbon-hydrogen bond. So this will not hydrogen bond. The next one, I have two CH3s attached to an oxygen. So that's like an oxygen with a CH3 and another CH3. And therefore, there's no oxygen-hydrogen bond in there because in reality, this oxygen is actually bound to the carbon. And I'm not going to take the time and draw the whole Lewis structure, but it's actually bound to the carbon like this. But if I look at this molecule, it goes CH3, and then I have a CH2, and then that's bound to a nitrogen, which has two hydrogens attached to it. And remember that one of the criteria is having a nitrogen, maybe a nitrogen hydrogen bond. Therefore, this molecule is capable of H bonding. Or I shouldn't say capable. That's not what the question's asking. Capable and has, so are two different things. So has H bonding. And there you have it. Okay, let's move on and talk about calorimetry. This one here, it says, given the amount of calories burned, the initial and final temperatures of something, so in this case it's water, calculate the mass of substance burned. So for the heat released in calorimetry, we use the formula Q is equal to M times C, which is specific heat, delta T. I think our book uses Q is equal to M times SH times delta T. So what that means is that SH is specific heat, which is the same thing as C. They're identical. The reason I like this version of it is because my students seem to find it easier to remember because it kind of looks like Q is equal to MCAT, and the MCAT is an exam to get into medical school. Anyhow, let's use this one here. Let's use this one, and we're going to rearrange and solve for mass. So mass is going to be equal to Q divided by specific heat times delta T. Remember that delta T, I'll write the formula up here. Delta T is equal to the final temperature, subtract the initial temperature. And they're telling us that it goes from 15 to 75 degrees Celsius. So it's going to be 75.00 subtract degrees Celsius, subtract 15.00 degrees Celsius. So that equals 60.00 degrees Celsius. Now I can plug my numbers in because I have my Q, which is my number of calories. I have my specific heat, and I have my delta T. So let's plug in some numbers here. So we have 3,000 calories. Okay. This one's kind of goofy because this number only has one sig fig in it. Kind of silly. Anyhow, we have our specific heat, which is 1.00 calories per gram degrees Celsius. And then we have our delta T. They took all this time to measure the delta T so carefully to have 4 sig figs, but they've only got 1 sig fig in their energy. What kind of person put this together? Anyhow, let's solve it. And when you do, you see that the units of energy cancel and the units of temperature cancel out, and we're left over with mass. So when you plug that in, you actually end up with 50 grams. Now, in order to express that with 1 sig fig, this is totally fine, totally fine. Or you could even write it in scientific notation, 5 times 10 to the 1 grams. That works too. Whatever makes you happy. Okay, be able to differentiate between chemical and physical process. Wow, this one really takes you back. This is one of the first concepts that we look at in Chemistry 101 is determining when we're dealing with a chemical change and when we're dealing with a physical change. So it says here, during a chemical process that bonds are broken, right? Not only are bonds broken, but bonds can also be formed, right? So you have to keep that in mind. And during physical processes, bonds are not broken. So for example, a phase change like boiling water going from the liquid phase to the gaseous phase, right? This is a phase change. That is not a chemical change. It says creates water vapor, not hydrogen gas and oxygen gas. Whoa, if it made hydrogen and oxygen gas, boiling water would be a much more dangerous thing to do. So boiling water, again, is when you take liquid water and you convert it to water vapor. And this is nothing more than a physical change. physical change. Boiling water for spaghetti results in deliciousness, not deadliness. If that isn't Dr. Garcia to a T, I don't know what is, okay? That is definitely her language, not mine. Number 21. Given the total pressure of a mixture of gases in a system, as well as the pressure of several individual gases, calculate the partial pressure of the missing gas. And for this one, you need Dalton's law of partial pressures. And if you're unsure, Dalton's law of partial pressures. In Dalton's law of partial pressure states that the total pressure is equal to the sum of the individual pressures of all the gases. So it'd be the pressure of the first gas plus the pressure of the second one plus, and so on and so forth. So that's Dalton's law of partial pressures. Now here's the question. It says, what is the partial pressure of water vapor? What's the partial pressure of water vapor in millimeters of mercury in an air sample when the total pressure is 1 atmosphere? So this is my P total, 1.00 atmospheres. And the partial pressure of nitrogen is 0.79 atmospheres. The partial pressure of oxygen is 0.20 atmospheres. And the partial pressure of all of the other gases is what? 0.0044 atmospheres. Well, we also need to determine the partial pressure of, I don't know why I wrote X when I meant to write, come on, plus X, and X will be our water vapor pressure. So in this case, you just solve for X. And when I solve for that X, you take 1 and you subtract 0.79, subtract 0.2, subtract 0.0044. And obviously, you're going to end up with a really small number. And that number is the pressure of my water vapor. So I could put here the pressure of water gas is going to be equal to 0.0056 atmospheres. Now you need to have, I think you need to have this conversion factor in your brain. I'm not 100% sure, but I think it's a good idea to know how many millimeters of mercury there are in 1 atmosphere. And there are 760 millimeters of mercury in 1 atmosphere. And so we can use that as our conversion factor. And so 1 atmosphere is equal to 760 millimeters of Hg. And our atmospheres cancel out, and we end up with the millimeters of, we end up with, what's it asking for? What is the partial pressure? Yeah, it's asking for it in millimeters of mercury. I don't think did I do it? Oh, I did. I just wrote down the wrong units here. So 0.0056 times 760 is 4.256. So I should only have 2 sig figs. So that equals 4.3 millimeters of Hg. I made a mistake here in my answer, so I'll fix it. 4.3 mmHg. Okay. Times 848. All righty, let's move along. It says here, given an element and the number of neutrons, determine the isotopic mass. And so bromine has an isotope that has 47 neutrons. What's the mass number of this isotope? So let's review here. When I have an element, if I have a number down here, this is my atomic number. And atomic number is the number of protons, right? And then if I have a number up here, okay, this is my mass number, and mass number is the number of protons plus the number of neutrons. Therefore, if I have an isotope that has 47 neutrons, what's the mass number? So my mass number again is equal to the number of protons plus neutrons. Well, I know that it's got 47 neutrons, so I'll start with that. how many protons does bromine have? Where would I find that? I would look on the periodic table, and bromine is element 35. Therefore, it has 35 protons. So it's going to be 47 plus 35. And when I tally that up, I end up with 82. So 82. And therefore, that is my mass number. This is the mass number. Okay. And so this would be the way that you would write that, it's not asking us to do it. It'd be bromine 82. And then, of course, I'm going to have 35 like that. Okay, so what's the take-home message from that question? Is that you need to know what mass number is, and you need to know what atomic number is, which I think most students master that relatively quickly. Number 23, even more practice on conversion factors. It says here, a solution is given to someone at a rate of 95 milliliters per hour. The stock solution has a concentration of 300 units for every 750 milliliters. How many units is the person receiving per hour? So it's just a matter of setting up the math correctly. So if I have 300 units for every 750 milliliters, and I know that I am giving it at a rate of 95 milliliters for every 1 hour, you can see that my volumes are going to cancel out. And when I take 300, so I'll do this, 300 divided by 75, which is 4. So 4 times 95 is going to be equal to 380. So I get 380, and my units will be units per hour. Units per hour, and that's it. This is just a matter of, doing a little bit of converting. And again, it's one of those situations where I would say, if you've done all the practice problems that I've, written or posted on D2L, you should be in very good shape when it comes to doing conversions. Okay, let's talk about bonds, different kinds of bonds. It says, what kind of bond forms between rubidium and sulfur? So the first thing we would want to do is we would want to find rubidium on the periodic table. So rubidium is element number 37. So element 37, and rubidium is in group 1A. Therefore, rubidium, we know is a metal, right? And what about sulfur? Sulfur is in the P block. Sulfur is element 16, okay? And it is a non-metal. So if I'm forming a compound between a metal and a non-metal, right? What kind of compound am I forming? I'm forming an ionic compound. So this compound would be, just circle the whole thing here. This would be an ionic compound. Okay? If I have a non-metal and a non-metal, I would get a covalent compound. Let's just pick an example off the top of our heads. Maybe something like CO2, right? Carbon is a non-metal. Oxygen is a non-metal. What about something like, I don't know, what if I have something like glucose, right? C6H12O6. Hydrogen is in group 1A, but hydrogen is a non-metal. So remember that. Hydrogen is a non-metal. Also, you should know the difference between a polar bond and a non-polar bond. So let's say, for example, in a molecule like water, right? If I draw the molecular geometry of water, we know that these are polar bonds because oxygen is more electronegative than hydrogen. Whereas what if I have something like bromine, Br2? This is a nonpolar compound because it has no dipole. There's no difference in electronegativity between those elements. Also, you should know the trends in electronegativity in the periodic table. So if I have my periodic table, right, electronegativity increases as you go up and it increases as you go across like this. So we'll put En for electronegativity. Fluorine is the most electronegative element. I believe that cesium is the least electronegative element, but that's neither here nor there. Okay, Number 25. If you're given an element, determine the number of valence electrons present. How many valence electrons do phosphorus, carbon, and chlorine have? Well, if I look at phosphorus, phosphorus is in group 1, 2, 3, 4, 5A. And phosphorus, if you look at, let's talk about the electron configuration of phosphorus. Maybe I'm making this more complicated than it needs to be, but whatever, sue me. So phosphorus, if I look at the noble gas that precedes phosphorus, it's neon. After neon, I have sodium, magnesium, aluminum, silicon, and then phosphorus. So I need to have 3s2 and then 3p3. So how many total valence electrons? I have 2 plus 3. So that gives me a total of 5 valence electrons for phosphorus. Carbon, I use a similar rationale. Carbon would have 4 valence electrons, and then similarly, I do the same kind of rationale for chlorine, and chlorine has 7 valence electrons. Review the terminology of the scientific method. So a theory, I'll write down just some definitions here. A theory would be a hypothesis supported by extensive testing. It's not yet considered a law. A hypothesis is an educated guess, right? That's what I learned in junior high school. Or you could say it's an attempt to explain an observation. There we go. And the last one, it says, what's a law? And it's a summary of a large quantity of information. Now keep in mind that this is a multiple choice exam, so you're not going to have to spit out an entire definition like this. You're going to have the definitions in front of you, so you should be able to discern between a theory, a hypothesis, and a law. So you should be able to tell the difference between those. Next question. Question 27 says, given an acid, determine its conjugate base. What is the conjugate base of sulfuric acid? Remember, if you have an acid and you put that acid in water, right, it's going to dissociate to form A-, which would be its conjugate base, plus hydronium, right? What's the definition of an acid? An acid is an H+ donor. That's the definition according to Bronsted-Lowry. And so this would be our acid. Why? Because it's losing a proton. Okay, water is behaving as a base in this case, but A- would be the conjugate base, right? This is the conjugate base. And if you're wondering, well, how the heck did you figure that out? Because when you think about the reaction in reverse, who is gaining a proton, right? A base accepts H+, and the A- is accepting H+ to form HA. And also H3O+, this must be our conjugate acid, because again, in the reverse reaction, it is losing a proton to reform water. So what would the conjugate base of sulfuric acid look like? So if I take sulfuric acid and I put that in water, right, sulfuric acid is going to donate a proton, right, singular. So if I write this down, and sulfuric acid is a strong acid, so I would be left with HSO4, not H2. And if I'm losing H+, +1, so if I have something that has no charge and it loses +1, it must have a charge of -1. So we'll just put HSO4-, and then of course I'm going to form hydronium like that. So the conjugate base, okay, the conjugate base, I'll highlight it, of sulfuric acid is hydrogen sulfate. Okie doke. And I made that video, so I'm sure you all know it, you know, frontwards and backwards. The next question says, remember, it says, given a cation, determine the number of electrons. It says, remember, for positive charges, you subtract electrons from the atomic number. So I have yttrium, which is element number 39. So Y is element 39. In case you're looking for it on the periodic table, it's element number 39. So that means it's got 39 protons and 39 electrons. So if I have Y3 plus, right, that means loses, let me write it a different way here. Y3 plus, therefore, lost 3 electrons. So it lost 3 electrons because electrons, remember, electrons are negative. Electrons are negative. So if you lose something that's negative, you become positive, right? This is something you would have learned either in grade school or junior high when you subtract a negative number, right? Lose something negative. It's the same thing as becoming more positive. Okay, the next one, again, is something that I'm sure you can all do in your sleep, but let's review it. It says, given the temperature in Kelvin, convert it into degrees Celsius, and therefore you should know the formula that the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273 or 273.15, whatever. And we could also rearrange this to solve for the temperature in degrees Celsius is equal to the temperature in Kelvin, subtract 273. So it says here, if the melting point of water is 273 K, which calculation would provide this temperature in degrees Celsius? And the answer is it would be this one here. And then if we plugged that in, we would say the temperature in degrees Celsius would be equal to 273 K, subtract 273, which would equal 0 degrees Celsius. And of course, that is the freezing point or melting point of water. Okay, review the states of matter quickly. We'll go over these. This is, again, something from the beginning of the class. We talked about the differences between solids and liquids and gases. In a solid, the particles are going to be very close together, very little molecular motion. They will have a defined shape, right? If you have a solid, it's going to have a shape. You know, it might be a uniform or a shape that's easily described, like a cube, or it could be a shape that's, you know, has no kind of, you can't describe it, you know. And we looked at how to determine the volume of a solid by submerging it in a liquid. That's something we did in the lab. Okay, so a solid, and solids are incompressible. Same thing with liquids. They're not, generally speaking, they're not easily compressed. They might be compressible to a very, very small extent, but generally speaking, they are incompressible, but they do not have a defined shape, right? A liquid will always flow and it will adapt to the shape of its container, whereas a gas doesn't have a defined shape and they're easily compressed. Why? Because gases are mostly empty space. Gases are mostly empty space. All right. The next one is question number 31. After this, we're going to take a short break. It says here that review the strong bases. Strong bases usually contain a group 1A metal and a hydroxide. So what would be strong bases would be things like lithium hydroxide. Lithium is a group 1A metal. Sodium hydroxide, potassium hydroxide, rubidium hydroxide. Right? These are the main strong bases that you're going to see really in Chemistry 101. All right, with that, let's stop and take a break here. And I am just going to stop the recording. So I'll put up 2 parts. Stop recording.